All right, hi everybody. My name is Hunter, and this is my second hot wash video, and I wanted to talk about epigenetics just because I've liked it ever since I took genetics at SUU. I just think it's really cool that we can modify how our genes express themselves more than just modifying the actual genes we have, and I think there's a lot of useful things that can be done with that. Something that we've gone over in class a little bit that I actually didn't know before, that I've enjoyed looking more into is histone modification, where we can add methyl, acetyl, or phosphoryl groups onto our histones, and that's going to change how the DNA binds to them, increasing or decreasing accessibility. So something we hit on hard, not really hard because we're going pretty quick, but is that if you change the polarity of a histone, so we make it have a neutral charge, then that negative DNA isn't going to want to bind to it as much, which is going to loosen it up and make it accessible so that we can replicate it or transcribe it, whatever we really need. Something cool that I found in this article that I was reading is how a lot of the modifications that are placed are interdependent. So if we look, for example, this probably isn't a real one, but it could be that anytime 5 is acetylated, that makes K12 also want to be acetylated as well. And that's going to change the modification or the activity of the whole histone even more. And then let's say since 5 was acetylated and then 12 was, that also made 17 gain a methyl or a citrate group or whatever that CIT is. So they work together as one thing happens, then that's going to promote more things. That suggests the existence of a histone code, which means that some underlying factors are controlling what gets modified and what doesn't, but we really don't know a whole lot about that yet. And the research um, is happening, and it could come up with some pretty cool things that allow us to modify genes more than what we're doing now, which is pretty cool. Um, Something big that happens directly on our DNA, our methyl groups are added by an enzyme DNA methyltransferase. So that's going to take the methyl group from an S-adenosyl methionine and put it on our cytosine groups from our DNA. So wherever there's a C, and there's also going to be a G, but that can be methylated. And then we're going to have islands of these cytosine um, nucleic acids, and all of those could be methylated together. They're likely going to be at a promoter region, and that's just going to block the promotion completely so that that area isn't going to be transcribed. I think I've got this going to show that right there. So we've got our methyl groups put on our cytosines. That's going to keep that the transcription enzymes from attaching to the promoter, and then no transcription is going to occur. So it's going to block that mRNA from being created at all. Um, and when I think of this in my head, I probably because I've been driving a lot recently, but let's say you're driving down a long road, you really need to turn right to get to whatever restaurant. You need to head east or wherever you're going. But each road that you come up to at that intersection, it's blocked off. Got orange cones, got cops. You keep going and it's blocked off and it's blocked off. If you have all these cops and these cones, you can never turn right. And that's the same thing that these methyl groups do, is they completely just block that transcription enzyme from attaching so that it can't go on to where it needs to go. Um, so this can happen by our natural processes. Our body is made to methylate certain areas of certain genes, and we're going to talk about that more on the next slide. But I also think what's almost more fascinating is that our lifestyles can cause excess or a lack of methylation. For example, if we have high levels of stress or we experience a big trauma, or if we have um, a good or bad diet, whatever it is, that's going to affect our methylation. And then excess exposure to smoke, like cigarette smoke, that's going to increase our methylation of our genes as well. And because of that, this methylation can actually be inherited by a person's children. So if you have a high amount of stress in your life and that's creating methylation, which is changing your phenotype, which is how your genes are expressed, that can be passed on to your child. And they can also feel more stress, or they can have these different expressions of weight gain or weight loss or anxiety or whatever it might be based on what you've experienced or the lifestyle you've created. That being said, I've used negative examples, but we could potentially in the future learn how to have positive methylation or demethylation so that our kids can have a better chance at life with lower anxiety, with healthier bodies. But the research is new. There's not a lot of data on it. I just think there's a lot of potential and it's really cool. Um, what our body naturally does, though, is it's going to methylate our genome so that certain genes are expressed in some cells and certain genes are expressed in others. That's how we get such a variety of cells in our bodies. And I just think that's super cool. And that's how we have a 100% of our genome in every cell, but they're all so different. It's mainly because of this methylation. In a sperm cell, you're going to have certain areas that are methylated so that it's a sperm, and then those areas would be demethylated, and others would be methylated in a nerve cell or a skin cell. Um, so our body is purposely doing this. Again, we don't know a lot of how it's regulated, similar to the histone codes, but our body is very tightly regulating our stem cells and their growth especially in our fetal stage, so that we can create all of the cells that we need properly, and then those can replicate, passing on their methylation to every cell that comes on after them. So that's methylation in a bundle, or not just methylation, but transcription regulation and the modification of our genes in a bundle. I think it's really awesome, and there's a lot of potential in the future to grow from that research. Thank you much.